us a lot about the science stuff. Professor Dave explains.
Hey everyone! Welcome to our exploration of one of the most essential yet often overlooked topics: how our body manages water and waste.
Did you know that your kidneys are like the body's own personal filtration system?
Water is not just something we drink. It plays a starring role in this entire process. Have you ever wondered what happens to a glass of water after you gulp it down? Let's unravel the mystery together.
Today, we'll dive deep into how water influences waste excretion and the incredible function of our kidneys. Get ready for a journey that will change the way you think about your body.
So grab your water bottles and keep your mind wide open.
Water is critical to life. About 60 to 70% of the body weight is made up of water. The body's muscle and kidneys are made up of 79% water. Water is an integral part of the body and its ability to function. In the context of waste excretion, water serves as a solvent that dissolves metabolites, toxins, and waste products, allowing the kidney to filter and excrete these substances efficiently. Without water, the kidneys would be unable to perform their essential function of maintaining internal equilibrium or homeostasis. This balance is crucial to the regulation of fluid and electrolytes level, blood pressure, and the removal of nitrogenous waste such as urea, which are byproducts of protein metabolism.
The excretory system, particularly the kidneys, is essential to filtering metabolic waste from the bloodstream. Blood enters the kidneys through renal arteries, which branch into smaller blood vessels until they reach the nephrons, the functional units of the kidneys. The waste excretion process begins here, where water plays a key role in dissolving waste products and excess ions, which are then filtered in the nephron tubules. The ureters transport urine from the kidneys to the bladder, where it is stored before being expelled via the urethra. This system functions primarily through filtration, secretion, and reabsorption mechanism, all of which rely heavily on water balance.
Each kidney contains approximately 1 million nephrons. A nephron consists of the glomerulus, a cluster of capillaries where blood filtration begins, and the Bowman's capsule, which surrounds the glomerulus. The primary filtration occurs in the glomerulus, where blood pressure forces water and small solutes like urea, creatinine, and ions into nephron tubule. Larger molecules such as proteins and blood cells are retained in the bloodstream. The filtered fluid or filtrate then travels through various sections of the nephron, including the proximal tubule, loop of Henle, distal tubule, and the collecting duct. Along this pathway, water and essential solutes are selectively reabsorbed back into the blood. The concentration of the urine depends on the body's hydration status, where more water is reabsorbed when dehydration occurs, producing concentrated urine. This process highlights the dynamic role of water in maintaining kidney function and fluid balance.
Water involvement in kidney filtration starts with its ability to dissolve substances that needed to be exerted, such as metabolic byproducts, drugs, and toxins. The filtration rate of the kidneys is referred to as the glomerular filtration rate, or GFR, which is regulated to maintain proper levels of water and solutes in the blood. When filtrate enters the nephron, it contains a mixture of water, ions, and waste products. As this filtrate passes through the nephron's tubules, around 99% of the water is reabsorbed into the bloodstream, along with the essential solutes like glucose, sodium, and potassium, leaving behind concentrated waste. A major regulatory hormone in this process is antidiuretic hormone, or ADH, also known as vasopressin. ADH increases the permeability of the nephron's collecting ducts, allowing more water to be reabsorbed into the blood. This is especially important during dehydration, where water needs to be conserved to prevent excessive fluid loss. Conversely, in conditions of excess water intake, ADH secretion is suppressed, leading to a higher volume of dilute urine being exerted.
The excretion of waste through urine is facilitated by water's ability to dissolve metabolic byproducts such as urea, creatinine, and uric acid. This nitrogenous waste derived from the breakdown of proteins and nucleic acid are toxic at high concentration and must be eliminated from the body. Water acts as a medium, allowing this waste product to be transported through the nephron and eventually excreted in urine. In a well-hydrated individual, urine is clear and dilute, containing low concentration of solutes. However, when water intake is low, the kidneys conserve water by producing highly concentrated urine. This is an energy-efficient way to maintain water balance while still allowing for the excretion of harmful waste. Chronic dehydration, on the other hand, can result in kidney dysfunction, including the formation of kidney stones, which occur when urine becomes supersaturated with minerals like calcium and oxalate.
The kidneys regulate water balance through osmoregulation, a finely tuned process involving feedback mechanisms. When plasma osmolarity, or concentration of blood solutes in the blood, increases, osmoreceptors in the hypothalamus detect the change and stimulate the release of ADH from pituitary gland. ADH increases the permeability of the nephrons collecting ducts to water, facilitating its reabsorption back into the bloodstream, thereby lowering plasma osmolarity, and this results in a smaller volume of concentrated urine being produced. If water intake is excessive, osmoreceptors signals the suppression of ADH secretion, allowing the kidneys to exert a larger volumes of diluted urine. This negative feedback loop ensures that the body maintains a stable internal environment, crucial for cellular function and metabolic processes. Furthermore, other hormones like aldosterone also contribute to the regulation of water balance by controlling the reabsorption of sodium, which indirectly influences water retention.
Adequate water intake is essential for maintaining kidney health and preventing diseases. Dehydration can impair the kidney ability to filter waste and regulate electrolytes.
The recommended daily water intake varies among individuals based on factors such as age, weather condition, physical activity, pregnancy, breastfeeding, or illness. People who engage in strenuous physical activity or reside in hot and humid climates generally require more water than those who are in sedentary or in cooler weather. On average, daily water intake should not fall below 8 glasses. But each person should adjust based on the factors mentioned earlier. Monitoring urine color is a helpful indicator. If urine appears dark yellow, it may indicate insufficient water intake. However, individuals with reduced kidney function, especially those with late-stage kidney disease or undergoing kidney treatment, may need to restrict water intake more rigorously. This is particularly crucial for patients on dialysis or with other kidney-related conditions. Therefore, strict monitoring and adherence to water restrictions may be necessary.
While hydration is important, drinking excessive amount of water can indeed have adverse effect on body. If the intake surpasses the kidney's capacity to excrete it, it can lead to electrolyte imbalance, often resulting in low sodium levels. This imbalance can affect the nervous and muscular systems, leading to symptoms such as confusion, muscle cramps, pale skin, fatigue, and weakness due to the kidneys working beyond their capacity. Athletes, particularly marathon runners and triathletes, who rapidly consume large quantities of water exceeding 6 to 10 liters might experience abnormalities in electrolyte balance. In extreme cases, this can lead to seizures, loss of consciousness, or comatose. Signs and symptoms of dehydration in adults may include low blood pressure or hypotension with high heart rate, muscle cramps, dark-colored urine that has a strong smell, loss of appetite, tiredness, headache, or constipation.
Long-term dehydration may lead to chronic kidney disease, a condition characterized by the gradual loss of kidney function over time. When the kidneys are unable to excrete waste effectively, toxins accumulate in the blood, leading to a range of health conditions including hypertension, cardiovascular disease, and kidney failure. Kidney stones are another significant health risk associated with insufficient water intake. When urine becomes too concentrated, it can lead to the crystallization of minerals such as calcium, oxalate, and uric acid. Over time, these crystals form stones that can cause severe pain, obstruct the urinary tract, and lead to infections. Increased water intake helps dilute urine and prevents the formation of stones. Maintaining optimal hydration also protects against urinary tract infections, which occur when bacteria enter the urinary system. By promoting regular urination, water helps flush out bacteria and prevent infections from developing. Common health diseases and conditions associated with insufficient hydration include kidney stones, urinary tract infection, chronic kidney disease, acute kidney injury, hyponatremia, fluid retention, impaired waste excretion.
Water plays an indispensable role in the kidney ability to filter waste and maintain overall fluid balance. It acts as a solvent for waste products, facilitates filtration and reabsorption processes, and enables the kidney to regulate the body water levels through hormonal feedback mechanism. Adequate water intake is not only essential for efficient waste excretion but also critical for preventing kidney stones, UTI, and chronic diseases. Ensuring proper hydration supports kidney health and prevents the harmful effects of dehydration.
Remember their motto, kidney function is not a right, it's a privilege.
He knows a lot about the science stuff. Professor Dave explains.